Hi, and we're going to start Chapter 10 today. I'm on page 626. Chapter 10 is quadratic equations and functions. We're going to start off in section 10.1. I guess you can turn ahead right now to page 6, actually 628. And I wrote a little bit of a different title here than they did in the book, and I'm going to go through why I did that here in just a second. The title in the book is Graphing y equals ax squared plus c. What I'd rather call this is we're not going to graph, we're going to sketch y equals ax squared plus bx plus c when b equals 0. And the reason I want to teach it this way is if you quickly just peek ahead to page 635, if you need to stop the video, look at page 635, look at the form of that equation. It's exactly what we have here. So I want to show you that what we're doing in section 10.1 is exactly the same thing as what we're going to be doing in section 10.2. It's just that in section 10.2 we will have a b value. In section 10.1, since b is 0 wipes this out and it leaves us with y equals ax squared plus c. Alright? So that's why I want to just refer to it in this way. We're graphing this equation, but when b is 0 in this case, or actually sketching it. So let's talk about, first of all, this chapter is entitled Quadratic Equations and Functions, Chapter 10. So what's a quadratic function? Because we haven't used that term before. A quadratic is a function of the form, which what we have here, y equals ax squared plus bx plus c. Now, this should look familiar to you because we were factoring those all throughout the end of the last chapter in Chapter 9. In other words, it's a second-degree equation. So second-degree equations or functions are called quadratics. Remember, any function with an exponent will graph a curve. Now remember, when I say an exponent, I mean something other than first power. Like this is a second power or second-degree equation or function. That means it's going to give me a curved graph. So what type of graph does a quadratic give us? So when we have a second-degree equation or function, what kind of graph does that produce? Well, it produces a U-shaped graph called a parabola. All right? And we're going to look at the most basic kind of parabola here in a second. It's the parent function, which is the simplest of all of these. It'd be y equals x squared. That's the parent function of all quadratics. So y equals x squared means that, maybe I should write this here on my video, that means that a equals 1, b is 0, which I told you all the functions today will have b equals 0, and in this case c also equals 0. So let's look at the parent function of quadratics right now. And that's the most basic, y equals x squared. This is the parent function again. So let's actually graph this. So I'm going to do this with you. Made a table. And I'm going to plot some points in my table. So let's pick the easiest. Let's always plug in 0 first. 0 squared, 0. If I plug in 1, 1 squared is 1. But here's the neat thing about squaring a number. If you plug in 1, you get 1. But if you plug in -1, -1 squared is also 1. If you plug in 2, 2 squared is 4. If you plug in -2, -2 squared is still 4. And if you plug in 3, 3 squared is 9. If you plug in -3, -3 squared is 9. Well, let's start plotting those points. Here's 0, 0, and 1, 1, and 2, 4, and 3, 9. And then you have -1, 1, -2, 4, and -3, 9. And you can see here's that U-shaped type graph that I was referring to earlier in my video. That is called a parabola. Any second-degree equation will produce a parabola. Now, there's a couple important things about this parabola vocabulary that we should know. The highest or lowest point of a parabola is called its vertex. The vertex of this parabola is 0, 0, which I guess I should add one other thing to my video right now as I'm mentioning that. Since the lowest point is at 0, can you see how the lowest point is at y equals 0? This graph would have a minimum, and its minimum is at 0 right now. You notice this graph has no maximum. It keeps on rising forever, but the lowest it will go is to y equals 0. So it has a minimum of 0. And then there's a second important vocabulary word that is applied to this. And I did this in red, not because red is wrong on this slide, but just to give you a different color that will show up nice. Every parabola has a line, an imaginary line that passes through it that divides the parabola into two symmetric parts. Remember, symmetric parts mean that they're mirror images of each other. And this line is called an axis of symmetry. So the axis of symmetry always goes through the vertex of any parabola, and any parabola, the left side of it is a complete mirror image of the right side. For any parabola, that would be true. So every parabola has an axis of symmetry, and that axis of symmetry has to pass through the vertex. So this parabola, the parent function, I drew it. It has a vertex at 0, 0. It has a minimum value at 0, and it has an axis of symmetry, and that axis of symmetry is at x equals 0. Maybe I should write that equation down. The axis of symmetry for this is at x equals 0. This is the line, remember, x equals 0. All right? Now, what I want to spend some time on next is in this section. This section is called graphing y equals ax squared, and maybe I should quickly erase this if I can and put in here plus bx in blue, plus bx plus c. Now remember, I called it this because right now b is 0, and since b is 0, I guess you could essentially say that's not there, which gets us back to what we were just talking about. You now know what y equals x squared looks like. What I want to investigate next is what would happen if a is 2. How would y equals 2x squared compare to just the parent function? How would y equals 4x squared compare to the parent function? What about y equals 5x squared and so on? So let's do that. Let's take our calculator out. You can see here I've taken my calculator out. I would encourage you to be doing this as I'm doing it on yours. Okay, so let's type in y equals x squared and x to the second power, and I'm going to graph it and just let you see that there's that parabola I just did on my previous slide. Okay, let's not change that, but let's go and let's try and see what happens if we have y equals 2 times x to the second power. Now remember, I didn't use parentheses here. We learned about this earlier on in the year. In Chapter 8, if I do not use parentheses, the second power only applies to x. It doesn't apply to the 2's. But let's see what the value a of 2, or a equals 2, would do to my graph. So there was the original parent function. Oh, do you notice how this is a little bit thinner or narrower of a parabola? Now, thinner or narrower is not the mathematical terms that we want to use. What we want to say is, and you've heard this term before, the parabola just got stretched by a magnitude of 2. That's what we would write on paper if I said, how does the value a equals 2 affect this graph? Well, it stretched the parent function parabola by a magnitude of 2. Okay, so now I think the next thing I had on that previous slide is what happens if I had an a value of 3. Let's try it. 3x to the second power. And let's see what happens there. And you can see it's even stretched a little more. Or what if I did y equals 5x to the second power? And you'll notice when I do that, that this is even stretched more. Okay? So hopefully you are getting the concept that the higher the value for a, the more the graph is being stretched. Now that shouldn't be anything earth-shattering, honestly, because when you think about it, we have learned that concept in many ways this year. Remember when you had slope-intercept form? That was the parent function in slope-intercept form. But if I had 2x, my graph had a stretch to it. If I had 3x, my graph was stretched even more. The only difference is I'm not working with a, remember these equations are linear, y equals mx plus b. The only difference is I'm now working with a quadratic. Okay, so we've learned these concepts before. So if I have y equals x squared, if I have 2x squared, this is just going to be stretched. All right, so I think we've just answered what would happen if I have an A value of 2, 4, 5 that's just going to stretch the graph more. All right, what happens if A is negative? Let's investigate that next. All right, so let's say that A is negative, and I want to see what happens in this case. So let me go back here, and let me clear these equations out that I had. And let's try and see what happens if we put a negative value in for A. So let's just try negative 1 first. I'll have negative 1x to the second power. And if you think about earlier in the year what we learned, you might already know the answer to this. Let's see what happens if I put a negative value in front and I graph. There's my parent function. And oh, the negative value just reflected the graph. Let's try what happens if I plug in negative 2x to the second power. Let's see what the negative 2 does. And if you remember from earlier in the year, the negative should reflect it, and the 2, from what we learned earlier in this video again, and reinforced, it ought to stretch the graph. Let's see if that's happening. There you go, reflected and stretched. So that's what we just figured out would happen if A is a negative. And then there's one final scenario that we have to cover. What would happen if A is a fraction between 0 and 1, like half or negative 2/3? You already ought to know the answer to this. You might want to pause the video and think about it before we actually do it on the calculator. All right, so going to the calculator. You already should know what would happen. We've already actually done that in more than one circumstance this year. What happens when A is a fraction? So let's put in a fraction, like 0.5, a half. So I'll try half x to the second power. And if you remember from earlier in the year, fractions should shrink the graph. Let's try it. There's my parent function. And there you go. There's your shrink. This is opening more slowly, and it's widening. Okay? So we've learned and applied all these at several different points this year. In fact, if I go another slide ahead here, we were talking linear and quadratic. I forgot one. We also used that when we talked about exponential functions. Remember, exponential functions were in this form? You know, if I just had, like, let's say, 2 to the x power, that's exponential. But if I did 2 times 2 to the x power, this 2 stretched the graph again. If I put a fraction in front, like a half, that would just shrink the graph, just like what is occurring here. Okay? So we have seen what I'm talking about here in linear equations. We've seen them in exponential equations. Now we're looking at them in quadratic equations. So we've seen instances of this many times over now. So that should get us going on what the value of A and what the value of A can do to our quadratic. If A is greater than 1, it's going to stretch the graph. If A is a negative, if A is negative, it will reflect the graph, reflect it. And if A is a fractional amount between 0 and 1, it will shrink the graph. In combinations, like if A was negative 6, the 6 stretches and the negative reflects the graph. All right, so the next thing. What happens if the value for C isn't 0? Let's take a look at that. So what happens if C was a 2? So instead of having y equals x squared plus nothing, what if we had y equals x squared plus 2? What does the 2 do to the graph? Or what if C was 3? So that's the next thing to investigate. So let's go back to the calculator and investigate those scenarios next. So let me clear those. So I have y equals x squared. And that's my parent function. I'll just graph that one more time, and you've seen that already. So let's try what happens if we have that C value become a 2. So I have x squared plus a 2. What does that plus 2 do? Well, when I graph, you notice it's the same parabola, but its vertex is 2 units up on the y-axis. So that's what a C value of 2 does. Let's see what happens if I have a C value of 3. X squared plus 3. Now it's the same graph, but you notice it's been translated 3 units up the y-axis. Let's try one more. What happens if x if C was negative 5? Before you graph it, you might want to make a prediction. So think about it. If C is negative 5, what do you think that's going to do to the graph? And if you said it's going to shift or translate the graph 5 units lower, you are correct. 1, 2, 3, 4, 5. You can see it. So now we've just learned how C can affect the parent function. All right? The value for C just takes the vertex and just shifts it up or down the y-axis. So with that said, the next thing I want to do is go through how do we sketch a graph. And sketching a graph means something different than actually graphing. Okay? Sketching means that we don't actually take out graph paper. We're not going to plot points and make a bunch of tables, but we're just going to basically draw a general picture and label a few points on this picture to support it's the correct graph. So sketching is not technically, it's like graphing, but it's freehand graphing. It's not as technical as graphing. It's not where I'm not going to have you graph 10 points on graph paper and make sure that every one of the 10 points are in a perfect spot. Okay? When you sketch, there are a few rules I want you to follow. Your picture should look accurate. You should label your vertex. And you should label 2 other points on your sketch. You should determine whether the graph has a maximum or minimum and give the maximum or minimum value. So I'll actually walk through those steps here in a minute. Okay, so we're going to draw an accurate looking picture. We're going to label the vertex, label 2 other points, determine whether the graph has a maximum or minimum, and give what it is. So let's go to number 26. And so in the bookwork, in the directions on number 26, it says graph the function. Whenever it says graph right now in this chapter, we can replace the word sketch. So when you see like in numbers 6 to 21 it says graph the function, compare the graph with the graph of the parent function, I will let you sketch these. Okay? And it's the same thing with numbers 24 to 32. They're going to ask us to graph the function and compare the graph with the graph of the parent function. So let's graph 26 first. So here's the first thing I notice. I notice 2 things right away. I noticed that, well, actually, I should put 3 things. I noticed 3 things. A is 2, C is negative 12, and of course, B is 0. All right, so since A is 2, from what we just talked about on our video, I know that this graph is being stretched when in comparison to the parent function. It's stretched. That's what a value of 2 for A does. And then think about negative 12. Negative 12 translates the vertex 12 down. 12 units down. Okay, that's what that does. So now, when I go to sketch it, I know that my vertex is at 0, negative 12. Since 2 is a positive, I know my graph, my parabola, has to open upward. And all I need to do is label a couple other points. Well, how do I figure out 2 other points? Very simple. Just pick an easy value for x, plug it in, and solve. So I already know when I plug in 0, I get negative 12. That's what this point means. So the next easiest thing to try to plug in would be 1. So I'll plug in 1. 1 squared is 1. 2 times 1 is 2. And 2 minus 12 is negative 10. That's where I'm getting 1, negative 10 from. Now, do you remember from earlier in the video, if you plug in 1 and get negative 10, when you plug in negative 1 and square it, you get 1 again. 2 times 1 is 1 minus 12. You're still going to get negative 10. Remember, whatever you plug in for the positive value, it will reflect for the negative value. So you don't even really have to overwork that. This is definitely opening up because A is positive, and this parabola has a minimum value of negative 12. I have a longer note here I want to read through with you, and this is why I'm introducing this now. In the next section, this is for 10.2, this is for section 10.2, there's a formula you can use to always find the axis of symmetry. The axis of symmetry is that line that mirrors the 2 sides of this parabola. Now, for this particular problem, we already know the axis of symmetry. The vertex is at 0, so my axis of symmetry And let me actually draw that. My axis of symmetry for this problem is going to be right here. It's going to be right down the y-axis. The axis of symmetry is at x equals 0. Okay? Now, for this problem, I don't need any formula to figure that out. But when we have a b value other than 0, which we will starting in our next section, you use a quick little formula to figure out the axis of symmetry, and it's this formula. The equation x will equal whatever negative b over 2a would work out to. Now you might be like, where does this b and 2a come from? Well, the b is right here, I'll circle it, and the a is right here. So let's try that for this problem. Now we already know that the axis of symmetry for this problem is x equals 0. So if I actually wanted to use that formula, I'd plug in 0 for b, which would make the numerator 0. I'd plug in 2 for a, which would make the denominator 4, and 0 over 4 is 0. So my axis of symmetry has to be x equals 0, and there is the axis of symmetry. All right? So I wouldn't need to use that formula for this problem because b is 0, and as soon as b is 0, the entire equation would be x equals 0. But starting in the next section, we will definitely use this formula to find the axis of symmetry. Let's go to 29 and try that. So in 29, we have y equals 3/4 x squared minus 3. Okay, couple of things I notice immediately. All right, and before I even address this, maybe I should turn that layer off. Let me just write these in. I notice that a is 3/4. I notice I have b equals 0. And I notice c equals negative 3. So the first thing is I know this graph has a shrink to it because I have a is 3/4, and I know the negative 3 means move vertex down 3. And maybe I didn't speak that well as a math teacher. I probably, instead of saying move vertex down 3, which is exactly what we're doing, I should say we should translate the vertex 3 units down. Now, I can find the axis of symmetry real quick. Now, in this problem, I know it's 0 because think about it. If I plug in 0 for b and I plug in 3/4 for a, I get negative 0 over 2 times 3/4. Well, 0 divided by anything is 0. So the axis of symmetry would be, and I'll draw it up real quick, the axis of symmetry in this problem is right down the y-axis. Okay? Now, my vertex has been shifted 3 units down. And since my vertex is shifted 3 units down, I know my vertex is at 0, 3. I drew that, or I wrote that here. So this is 0, 3. And I'll label that here in a minute. And then, since this parabola has a shrink to it, a shrink means it's opening wider. And since it's opening wider, I'll make it look like it's opening wider. So the parent function might look something like this, starting at 0, 0. And it just is opening normally, okay? Where this function is opening more wide, it's being shrunk, and it has a vertex at 0, negative 3. Now, I got to pick 2 other points to label. Now, I want to talk about this. When you have fractions, if you plug in 1, it's going to not make things as convenient here, because if you plug in 1 and square it, 1 squared is 1, 3/4 times 1 is 3/4, and guess what? Now you're working with fractions. So it's really easy to not have to work with fractions or to get rid of the fractions. Do you see how the denominator is 4? If you plug whatever the denominator is for x, I guarantee it will make the fraction disappear. So let's do that. 4 squared is 16. If I plug in 4, I get 16 here. So let me write this down. 3/4, if I plug in 4, 4 squared, 16. Now think about it. Doesn't 4 go into itself once and 4 go into 16 4 times? And yes, it does, right? And so then from there, since I have that, 3 times 4 is 12, and 12 minus 3 is 9, which tells me I made a little mental mistake here when I drew this up originally. I got to erase. This is not the point 412, it's the point 49. 49 is correct. Okay, and then if that's 4, 9, then this would be negative 4, 9. Okay, so that's what we can do to make sure our fractions disappear. if the denominator is 4, just plug in a 4 here, and you notice you're going to get 4, and this will create 16, and you have a simple cancellation. 4 goes into itself once, 4 goes into 16 4 times, and now we have a simple problem to solve without the fractions being involved. Don't forget at the end, we want to label the minimum. The minimum is -3, and my axis of symmetry in this problem is x equals 0. Okay, let's do one more here. 32. In 32, do you notice how A is -2/3, C is 9, B is 0? So there's a couple things I immediately notice from what we talked about earlier in the video. I have a reflection and a shrink, reflection and shrink here. That's what the A is telling me. -2/3 means we reflected negative, shrink is 2/3. And then C is telling us if C is 9, that means vertex moves up 9. Okay? Moves up 9 units. So it was translated 9 units up. B is 0, and if B is 0, remember, that tells me that my axis of symmetry is right here on the y-axis, because whenever B is 0, when I use that little formula, it's going to automatically give me 0 for response. So let me quickly label my axis of symmetry right there. And there's my vertex at 0, 9. I told you the vertex shifted 9 units up. And then the -2/3 is telling me that this should open down, and it should open more widely. It's being shrunk. So opening down and more widely. And then remember, since I have a fraction and 3 is in the denominator, if I plug 3 in for x, it's going to make this fraction disappear. Let's actually work that out so you can see it. So I have y equals -2/3. If I plug in a 3 here, 3 squared is 9, plus the 9. And if I take -2/3 times 9, that's -6, because remember, 3 goes into itself once, 3 goes into 9 3 times, and -2 times 3 is -6. And -6 plus this 9 is to give me 3. So if I plug in 3, I got 3, which means if I plug in -3, I get 3. Okay? So this has a maximum of 9. I wrote it over that. Let me just write it up above here. This graph has a maximum value of 9. And this parabola is translated 9 units up the y-axis and is reflected and has a vertical shrink of 2/3. Okay? Now remember, the parent function would have looked like this. It would have started at 0, 0 and just opened up, and it's certainly not going to be as wide as this one because this was shrunk. Okay, and then let's do one last question. 34, they ask us to, it says, tell how you can obtain the graph of G from the graph of F using transformations. Well, first of all, here's the graph of F. Let's talk about this one first. And the graph of F has an A value of 1, right here. It has a B value of 0, and it has a C value of -5. So remember, 1 means it's the same as the parent function, same, no stretch or shrink, no reflection. But -5 means the graph has been shifted 5 units down. So I'll do that. There's f of x. Now g of x has an A value of 1, a B value of 0, and a C value of 8. So the only difference between the two graphs is this first graph is 5 units down for the vertex, where this graph is 8 units up. So the question is, how do I get the graph, the g of x, from here? What do I do to translate? Well, do you notice that to make this graph, f of x, into g of x, what I need to do, and I'll do this in red just because it will show up nice, I need to take this graph and just translate it 13 units up. I'll just translate 13 units up. If I translate f of x 13 units up the y-axis, it will create g of x. And that's just what I put here. Okay? So that's how I can take f of x and create g of x. If I just take f of x and I can just push it 13 units straight up the y-axis, I'll get the exact same graph. It's just now it will be 8 units above the origin, not 5 units below. Okay, I'm going to stop my video there. I covered a lot of things today. This section we'll spend a couple days on. If you have more questions, we can talk about those in class tomorrow.